All right, now we're looking at question 33. Use the following information to answer questions 33 and 34. Methanol is produced commercially by the catalyzed reaction of carbon monoxide and hydrogen, as represented by the following equation, where carbon monoxide plus 2 moles of hydrogen gas with a catalyst becomes methanol. They also tell us that our change in enthalpy is a negative 90.5 kilojoules, which, if you remember from the earlier questions in this diploma, means that this is an exothermic reaction. So we could put heat as a product. At equilibrium, the concentrations were measured as follows. Our concentration of carbon monoxide is 0.75, our concentration of hydrogen gas is 1.25, and our concentration of methanol is 2.75 moles per liter. The value of our equilibrium constant Kc is what? Well, we can solve for this. Kc is going to be our products over our reactants, the concentrations of these raised to the power of their coefficients. There's no coefficient, well, there's just a coefficient of 1 for the methanol, so it's just our concentration of methanol on top, and then it's going to be our concentration of carbon monoxide on the bottom times our concentration of hydrogen gas raised to the power of 2. So we can plug numbers into this. Our concentration of methanol is 2.75. Our concentration of carbon monoxide is 0.75. And our concentration of hydrogen gas is 1.25. And then it should be raised to the power of 2. We can plug these numbers in, and then we can solve for Kc. So let's pull up our calculator here. And we will do our top 2.75, and then we're going to divide by everything in the denominator within a bracket. So I'm going to start a bracket here for everything in the denominator. Then I'll have a bracket for 0.75, and then I'll have another bracket for our 1.25. Oops. 1.25 squared. That's our hydrogen. And I'll close off the bracket for the whole denominator. And we're going to end up with 2.35. But then they just give it to us in 2 significant digits, which makes sense because this only has 2 significant digits here, our concentration of carbon monoxide. So C is going to be our answer for our Kc value. They don't ask this in this question, but if we have a Kc value that's greater than 1, it means that we are favoring our products. Heating the equilibrium system represented by the equation above would shift the equilibrium toward what, and the value of Kc would do what? Well, that's why we put heat in our chemical equation. Remember that we shift away from increases. So we are increasing the temperature, so heat will increase. We will shift away from increases, which means the concentration of our reactants will go up and the concentration of our products will go down. So we're going to shift towards the reactants. So first of all, let's get rid of C and D. And if we shift towards the reactants, then we'll have more reactants and less products. If we look at our Kc calculation here, if we were to make our denominator larger with more reactants and our numerator smaller with less products, we would get a smaller Kc value. So we will decrease our Kc. We will decrease our Kc because we're going to end up with more reactants, so a larger denominator, and less products, a smaller numerator here. Let's continue on to our next page. Methane gas can be produced in a laboratory by reacting carbon disulfide and hydrogen gas, as represented by the following equation. Carbon disulfide gas plus hydrogen gas forms methane and hydrogen sulfide. Initially, at a temperature of 90 degrees Celsius, 0.18 mole per liter carbon disulfide and 0.31 mole per liter hydrogen gas are present in a closed container. When equilibrium is established, 0.13 moles per liter of carbon disulfide gas is present. The concentration of hydrogen gas present in the container at equilibrium is what? This is another rice table question. So let's set up our rice table here. I can extend my page, so I'm going to do that. Give myself a little bit more room. I'll rewrite the reaction so that I can put all of my concentrations below it. And now that I've given myself more room, I will use the space that I have. So our reaction, initial concentrations, change in the concentration, and our concentration at equilibrium. Our reaction is between our carbon disulfide gas and our 4 moles of hydrogen gas. We will end up with methane gas and hydrogen sulfide gas. 2 moles of hydrogen sulfide gas. Here's our reaction. I see that's slightly off the screen. I think I can go a little bit more to the right. Is that better? Nope. One more time. There we go. There's our reaction. Now, at a temperature of 9 degrees Celsius, we initially have 0.18 mole per liter of carbon disulfide and 0.31 mole per liter of hydrogen gas. These are our starting reactants. So I'm going to put those into this table here. We have 0.18 and we have 0.31. At the start, we don't have any of our products. Now the change that's going to occur here is based on the magnitude of the coefficients. Our reactants are going to go down for equilibrium to establish, so we will decrease our carbon disulfide by some value x, and because there's a coefficient of 4 on our hydrogen gas, we will decrease 4 times the concentration of hydrogen gas. Our products will increase, however. So our methane will increase by a value of x, and our hydrogen sulfide will increase by a value of 2x because it has a coefficient of 2. When equilibrium is established, we have 0, I'll use green here, 0.13 mole per liter of carbon disulfide. That means that 0.18 minus x gave us 0.13, which tells us that x has a value of 0.05. Now, they're asking us to find the concentration of hydrogen gas present in the container at equilibrium. We can find all of the gases present in the container. This question is asking for hydrogen gas, but if they asked you for another gas on the diploma, it's a good idea to know how to calculate each of them. We know what our x value is. It's 0.05, so minus 4x would be the same as saying minus 0.20. 0.31 minus 0.20 would leave us with 0.11 moles per liter of hydrogen gas, which is the answer we're looking for. So I'm going to put that in our blank here, 0.11 moles per liter. The others are going to increase by a value of x. So you're going to have plus 0.05, and then 2x would be plus 0.10. So the equilibrium concentration of methane would be 0.05 moles per liter, and our equilibrium concentration of hydrogen sulfide would be 0.10 moles per liter. And here are all of our equilibrium concentrations if we needed to find a Kc value. Next question. Here is a bunch of chemical species that are all based on boric acid, going to dihydrogen borate, hydrogen borate, and then the borate anion. In the list of chemical species, this ion, dihydrogen borate, and what would form a conjugate acid-base pair, and the amphiprotic species are what? Okay, a conjugate acid-base pair means that the one can become the other by an acid-base reaction. This could be a conjugate acid-base pair with either the boric acid above it or with the hydrogen borate below it. I'll do the acids in red, but the conjugate acid-base pair that could be formed first is the boric acid acting as the acid and this dihydrogen borate ion acting as the base. Or if it's acting as an acid, then the hydrogen borate ion, sorry, I forgot the charge here. The hydrogen borate ion would be acting as our base. Either chemical 1 or chemical 3 could be acting, could make it a conjugate acid base pair. So we can get rid of rows A and B because they only give us this option to have our hydrogen borate ion. And then the amphiprotic species are ones that can either accept protons or donate protons. That's going to be 2 and 3 here. This one can donate 2 protons and accept a proton, and this one could donate 1 proton and accept 2 protons. So D is our answer here. Borate is polyprotic. It can accept 3 protons, but it's not amphiprotic. It cannot donate a proton. Amphi means that it could go either way. It could act as an acid or a base. A student prepared 2 solutions with the same pH and added chlorophenyl red indicator to each solution. The student recorded the following information. Solution 1 has hydrogen sulfide, and it's orange at a pH of 6.6. Solution 2 has hydrogen sulfide and the hydrogen sulfide ion. It's orange. Then the student added a small amount of hydrochloric acid to each solution. After the addition of hydrochloric acid, what would you see? Which of the following rows identifies the observed color and the observed effect on the pH after the addition of a small amount of hydrochloric acid to each of the 2 solutions? First of all, I've been saying hydrochloric acid out loud, but they don't actually say that HCl is hydrochloric acid. So you should know that adding hydrochloric acid is going to decrease the pH unless something counters the pH change, like a buffer. Solution 2 has a conjugate acid-base pair, which means that it has a buffer. The buffer can resist pH change. Now they are making it clear that they're adding a small amount of hydrochloric acid, which means that if there's a buffer present, it'll have a negligible effect on the pH. So solution 2, we should see no real change in the pH. And if we have no real change in the pH, then there won't be a change in the indicator. So we're going to actually get rid of rows A. That's the highlight. I'm going to strike them out. We're going to get rid of row A and B because they show that the buffer solution has a change in the pH. We're adding an acid to this, which will decrease the pH. If we decrease the pH, this is, whoa, I did something that I didn't mean to do on the computer. It's okay, I'll be able to load back. Okay, we're back. If we're adding an acid, we're decreasing the pH. So already, this is the only one that makes sense here, that we're decreasing the pH. And then we can check our indicator color, though, from our data booklet here. It's a good practice. We'll check it. We'll find chlorophenyl red, and then we'll see what's the color in the more acidic environment and what's the color in the more basic environment. Chlorophenyl red here changes from yellow to red. So the more acidic color when you're below a pH of 5.2 is going to be yellow, and the more basic color is going to be red. So this makes sense that as we're getting more acidic, we'll change to the yellow color, the acid color. So C is correct here. But if these showed the same color and then they said increase, decrease, or if they both said decrease, then it's important to know how to use the table. Let's go to the next page here. This will be the last one for this video. Use the following information to answer numerical response question 14 and questions 37 and 38. Potassium sorbate, which has this formula, is used as a preservative in beverages to inhibit the growth of mold. The equilibrium formed when the sorbate ion reacts with water can be represented by this following equation. Although the potassium sorbate is added to the beverage, it is the sorbic acid that inhibits the growth of the mold. So it's this one here. I guess I forgot that I'm on my touchscreen. This is the one that inhibits the growth of the mold. And we have our base constant here of 5.8 times 10 to the negative 10. The value of Ka for sorbic acid expressed in scientific notation is A dot B times 10 to the power of C. Well, to get a Ka value, we should know that Ka is going to be Kw divided by Kb of the conjugate base of that acid. So if we know our Kb value here, then we can just take Kw, which is written in your data booklet. It's not a value you need to memorize, but you should be familiar with. I'm just going to show you where you can find it. Our Kw value is right here, 1.0 times 10 to the negative 14. And our Kb value is 5.8 times 10 to the negative 10, which, if we do this calculation, we'll do our, I'm going to put them in brackets because they're in scientific notation, 1.0 times 10 to the negative 14 divided by 5.8 times 10 to the negative 10. We're going to end up with a Ka value of 1.7. They just want it in two significant digits, times 10 to the negative 5. So on your numerical response, you would say 175. The amount of sorbic acid present could be increased by doing what? Okay, well, let's take a look at these. Adding HCl, adding NaOH, removing H2O, removing your sorbate. Okay, let's take a look. The solvent here isn't really part of our equilibrium expression because it's a liquid. It's not really part of our Ka value, but even if water was significant here for changing our concentration here, if we were to remove water, it would cause a shift to the left, which wouldn't change. I would decrease our concentration of our sorbic acid. If we remove our sorbate, the same thing. If we decrease, we shift towards decreases. And if we were to add NaOH, it would increase this, which would cause a shift to the left. So B, C, and D would all cause left shifts. These are all left shifts. However, if we were to add HCl, then we would react with our hydroxide and we would react with our potassium sorbate, which means that if we react with this, we would force this reaction to occur. This is a strong acid. HCl is a strong acid. This is basically like what you would do if you were titrating this base, is you are adding your H3O plus your sorbate. And because you're using a strong acid, this is a quantitative reaction that is just going to become your sorbic acid. This is a strong acid which would make, I'm going to say react with the conjugate base. So you would end up creating more sorbic acid. When reacted with sorbate, an acid that would produce an equilibrium that favors the reactants is what? Now, this is going to use the acid-base table, which my PDF here, I don't know if I have a good way of rotating it. Can I rotate this here? I don't know if I'm going to find that out right now. But if you have your data book with you, you've got this acid-base table, which is sideways on this here. But you're going to use it somewhat similarly to the redox table. If the acid on the table is below the base, then you are going to favor the reactants. So the first thing that we're going to do is we're going to figure out where on our table our sorbate is going to end up. And that's going to be based on our Ka value. Our Ka value is 1.7. Now, you'll have to twist your head to look at the screen, but you'd have to say, 1.7 times 10 to the negative 5. you'll have to find where it's going to end up on this table. Your stronger acids are near the top with your larger Ka values. So you're going to have to find it. It's going to be in right at the same point as this one here, which is our dihydrogen citrate ion. You can slot it into the table right here if you want, and then compare it to the other acids on the table. Or you can just pull the Kas for each of these acids off the table. And the Ka here, 1.8 times 10 to the negative 4. Our Ka is going to be 6.3 times 10 to the negative 5. Our Ka here is going to be 1.3 times 10 to the negative 5. And our Ka here is going to be 1.4 times 10 to the negative. I wrote a number here, but this is our let me pull up my data booklet here. You'll just have this great lull in the video here as I find where this one is. That is lactic acid. That's 1.4 times 10 to the 4 times 10 to the negative 4. We're looking for, this is our base here. This is our base. These are all of our acids. So for something, we want the acid to end up below the base. And this base is going to be with a conjugate acid that has a Ka that we calculated just in the previous step, equal to 1.7 times 10 to the negative 5. So any acid with a Ka less than 1.7 times 10 to the negative 5 will favor the reactants here, because it will be, in a sense, the a weaker acid than the conjugate acid there. If you're looking at all of these, only one of these is less than 1.7 times 10 to the negative 5, and that is C. This acid here is going to be the one that is less. That's our vinegar, our acetic acid. So that would favor the reactants. That's where we're going to stop the video here.